In this video, we're going to revisit using calculus for curve sketching. We did quite a bit of this back in chapter 3, I guess. Let's look again now that we've looked at limits at infinity. So the first 4 steps should be familiar to you. If we're going to take a look at the sketch, we're going to compute both the first and second derivatives because they tell us about increasing behavior of the function and concavity. Of course, if we want to know increasing, we need to find critical values and create the sign graph to determine exactly increasing, decreasing. We want to find concavity. We've got to find when the second derivative is 0 or doesn't exist and use that sign graph to determine the concavity. And then evaluate the function at those critical points and points of inflection since they're going to be key points on our graph. That's the same steps we did before. But now that we've got limits at infinity or infinite limits, we can look at the end behavior. So if say the domain is all reals, then we would look at the limit as x goes to infinity and x goes to negative infinity. And if those limits exist, then we would have a horizontal asymptote. However, if we had a bounded domain, well, we still would look at the endpoints, but now we'd look at the limit as we put a from the right, since that's the left endpoint, and the limit as x approaches b from the left, since that's the right endpoint. Again, if those limits exist, we've got horizontal asymptotes. Similarly, we can look at places where there might be discontinuity. So we're not guaranteed that this function exists everywhere. So at any point where we've got a discontinuity, we would look at that limit. And if that limit, if it equals plus or minus infinity, then we're going to have a vertical asymptote. So that's how to interpret the results. So if as we go to the endpoints and the limits exist, we have a horizontal asymptote. And if at places where we've got discontinuity and the limit has to be plus or minus infinity, then we have vertical asymptotes. And then we'll take all that information, put it together, and sketch the graph. So let's look at an example. Forewarning here, I'm going to skip a lot of steps in the calculations of derivatives. I'll even be kind of fast in my evaluations of limits, just because there's a lot of steps, and if I went through everything in all its gory detail, which you need to do when calculating these so you don't make mistakes, but if I were to do that, these videos would be way too long and you'd be asleep before we got to the end. So just keep that in mind. I'm going to skip a lot of steps, but hopefully you can follow along. So let's look at the example where f of x is equal to x squared divided by x squared minus 1. And I'm not putting any restrictions on the domain. However, by definition of the function, we know that the bottom cannot be 0. So first off, we need to determine what's our viable values we can put into f. So we know that x squared minus 1 can't be 0, which tells me that x squared cannot be 1, which tells me that x squared cannot be plus or minus 1. Whoops, not x squared, but just x. So, so now we actually know what our domain is. Our domain is going to be, whoops, that's a little too big. Our domain will be the range negative infinity to minus 1, union minus 1 to 1, and then 1 to infinity. Okay, and at plus or minus 1 are spots where we have discontinuity, so we will have to come back to that and look at those. So our derivatives, so let's look at f prime of x. So like I said, I'm going to speed this up. So this is a quotient rule, but if we computed the derivative, we would get negative 2x divided by x squared minus 1 quantity squared. And our critical values will be when this is 0 or doesn't exist. Well, the places where it doesn't exist are exactly outside of my domain, plus or minus 1. So my critical value will just be 0. But I will have to take into account plus or minus 1 when I do the sign graph. So my critical value is just 0. And so let's go ahead and make the sign graph for that. So we look at the sign graph. We're at -1, 0, and 1. Those are where the graph can change its signs. And if I put this all in, f prime is, let's see, if it's less than -1, then it's positive. Not at all. If it's less than negative, oh yeah, sorry. If it's less than -1, it's positive. It's over here, it's positive. But it switches at 0 and it goes negative. Again, you do the work, plug in values, make sure that sign graph is exactly what you expect. What does this tell me? Well, it tells me my function is increasing up until 0 and then decreasing after that. And so I must have a max at x equals 0. That's going to be some max of my function. Now the second derivative, if I look at f double prime of x, again, we have to do quotient rule again with this, but what we would get is 6x squared plus 2 all divided by x squared minus 1 cubed. Now, if I look at places where this is 0, well, the top is never 0 because this is always positive, 6x squared is always positive, and 2 is always positive. This top is always actually bigger than 2. So the only places where it can change signs are when it's undefined. So I'll look at the sign graph for the second derivative. It's -1 and +1. And if I am less than -1, this will be positive. If I'm between -1 and 1, it'll be negative. And if I'm bigger than 1, it'll be positive again. So that tells me that it's going to have to be concave up in this region, concave down in this region, and concave up again. So now I know the concavity, I know the increasing, decreasing. Now I need to look at what's going on at the endpoints. So our endpoints are plus or minus infinity. So I need to take a look at what is the limit as x approaches -infinity of x squared over x squared minus 1. Well, this is perfect setup for L'Hopital's rule because the top's going to infinity and the bottom's going to infinity. And so this is equal to, by L'Hopital's rule, the limit as x goes to -infinity of 2x over 2x, which, well, that's just a 1, and this is 1. The argument's the same. I'll let you do it by yourself, but if I take the limit as x approaches infinity of x squared over x squared minus 1, you can use L'Hopital's rule again and see that that's a 1. So there's the end behavior. I've got a horizontal asymptote, so a horizontal asymptote of y equals 1. Okay, so that's my end behavior. And then how about the behavior at points of discontinuity, which is plus or minus 1. So I'm going to look at the limit as x approaches 1 of x squared all over x squared minus 1. So the top's going to 1, so the top is infinitely close to 1. But the bottom is infinitely close to 0. So I've got a finite number divided by an infinitesimal, which is an infinite number. Plus or minus, well, actually depends on what side of 1 I am. So right now the best I can say is that this is plus or minus infinity, because I've got a finite number divided by an infinitesimal. So that means I'm going to have to look at left and right hand limits. So the limit as x approaches 1 from the left of x squared all over x squared minus 1. Well, the top is still, whether I'm to the left or right of 1, the top is still infinitely close to 1. The bottom's infinitely close to 0 as well, but I'm taking a value less than 1, squaring it and subtracting 1, which means the bottom will be negative, telling me that the limit is going to negative infinity. However, if I look at the limit as x approaches 1 from the right, so now I'm going to take values bigger than 1 of x squared all over x squared minus 1. The top is still infinitely close to 1. But now I'm taking values bigger than 1, squaring it and subtracting 1, so the bottom will be positive, telling me that my limit must be positive infinity. And running through the same argument, if I look at the limit as x approaches negative 1 from the left of x squared all over x squared minus 1, well, the top is going to be still close to 1 because I'm squaring negative 1. But now I'm taking values less than negative 1, squaring it, which means I'm going to be bigger than 1, and so the bottom will be positive, giving me that the limit is positive infinity. And if the limit as x approaches negative 1 from the right, so I'm going to be less than negative 1, x squared all over x squared minus 1, then the top still close to 1, but the bottom will be negative because I'm a little bit less than negative 1. I square it. I'm still going to be smaller than 1, and so that subtraction would be negative. And so this is negative infinity. So I know the behavior. I've got vertical asymptotes at plus or minus 1. So I should probably write that. So I have vertical asymptotes at x equals plus or minus 1. And I know exactly the behavior on either side of that. So putting this all together, let's just plot a general axis. So here's xy axis. The key spots are, where did we find critical value at 0? And I should probably put that into my function. What is f of 0? Let's work that over here. Well, f of 0 is 0, because it's 0 over 1, which would be 0. So I know that the function will cross right here. I've got asymptotes at plus or minus 1. So at minus 1, I'm going to have a vertical asymptote. At positive 1, I have a vertical asymptote. And I have a horizontal asymptote at y equals positive 1. So that's here. This is y equals 1, say. And so I've got a vertical asymptote at y equals 1. What else do I know? Let's go back to our sine graphs. the function is increasing up to 0 and then decreasing after that. So it is increasing up to 0. So let me just mark that on this graph so I know that my function is increasing up to there. So it's increasing. And then it's decreasing after that. So decreasing from then on forward. I also know about concavity. I know that it's concave up. When I get up negative infinity to negative 1, and it's concave up from 1 on. So it's concave up in this region. So we're going to say concave up. And it's concave up over here as well. Concave up. But it is concave down throughout here. Concave down. And that's enough. I can put this all together into my graph. And so it's concave up and increasing. Oh, well, actually, we computed these limits. Let's put them to use. As we approach negative 1 from the left, so that's to the left of this line, it's going to positive infinity, so it's going to infinity that way. But as on the other side, it's going to negative infinity, so it's going down. At 1 from the left, it's going to negative infinity, and from the right, it's going to positive infinity. So from the left, it's going to negative infinity, and from the right, it's going to positive infinity. So putting the finishing touches on this, let me erase this because it's in a bad spot. So finishing touches, all right, it's increasing, concave up. Does this graph cross the horizontal asymptote? Well, let's just logic it through. If it did, well then it would have to turn around and go back up. But this region right here, it's decreasing. But my function has to always be increasing. So this can't happen, which tells me that the graph approaches it but can't ever cross it, and so must look something like this. How about on here? Well, between negative 1 and 1, my function increases up until it hits the max right here at 0, and then it decreases after that. It's also concave down, so there's no changes in that. So my graph has to go up, hit there, and come back down, and go there. And the last little bit, it's concave down and decreasing, which means, again, it can't cross this horizontal asymptote because if it did, it would have to increase. And so the graph has to look something like this. And that's the graph of y equals x squared all over x squared minus 1.